Inconspicuous.
I don't know why.
Hey, this
the neck on her.
Oh no, he will sit up there and lecture and like at some point he'll say, yeah, pay attention to this. I'm gonna connect on this. And you'll show up and it'll be the same shit, but like two numbers will change. Oh my god. Well, like two numbers will change. Let me send it to you later. I'll see your make.
Okay, so next chapter is the curve and surface theories. And most likely we've finished pretty much our study on the modeling schemes and then some of the basics of the geometric transformation by mapping. Now we are ready to move on to the curve and surface theory. And the importance of this is because most of the modern technology, modern parts, if you go to industry, you will see a lot of curves added on, especially the aerodynamic curves on the vehicles, airplanes, the underwater, all this required is curve. So you should be a master of the curve to be able to handle or make things not only just for the nice and beautiful, but also make it function as it is in your intention. So what we will do is here is that we will study the cubic spline first of all in this section. And then the second one is B for beta spline. Third one is surface. Okay. So after you finish this chapter, you will know what is the theoretical background or theoretical fundamental ground to build up those curves that you can find on the AutoCAD inventor. There are a lot of different curves in there. Mostly spline curve, cubic spline curve, B-spline curves, and you will see the difference. And you should be able to apply the right curve into the right part, okay? So we'll start with the data structure before we can study all this curve, spline curves. Start with the data structure first of all. The reason why we do this is because a lot of mathematical formulation will be done in matrix form. So I'm going to show you how do we formulate those data, like the points or lines or the planes or surfaces, in the format of the matrix. Okay. So first of all, the point usually goes with the x, y, z. We have seen already in the mapping and transformation. And then the line usually goes with, if it is a plane, xy plane, you go with the simple equation of y is equal to what? Ax plus b, right? X plus b. That's a general forms. But in order to deal with this in computer, what we will do is to transform this into further simplified forms like ax plus b, y plus c is equal to 0. Okay. And then in matrix form, we actually present this A, B, C multiplying 2, x, y, and then 1, all is equal to 0. So computer actually understand line, some line as a function in the form of matrix like this. Okay? And then if you are dealing with a plane, some line is space. The plane equation usually is going to be the extension of the line like this. And then again, if you present this in matrix form, and then x, y, z, and 1 all is equal to 0. That's the matrix form of the plane. Okay, the computer understand. So with these data structure, we can talk about some of the important things about the actual implementation of these. For example, the line, such as take a look at the line first. Line, because we're talking about curve, it is all branched out from the line. So what we will do is to focus on the line and let's see how the computer actually understands and present those things in the screen. So the way we actually, the format that we use is a parametric line. It's a little bit different from the mathematical formulation. It is a more practical expression of the line that the computer can understand and then present lines on the screen. So the way that they use here is that the symbol R, and the parameter lambda, R1 plus 1 minus lambda, and R2. If you look at this, there are a couple of things that you have to know about. R1, R2, these are what we call control points. Control points mean that you click those two dots to connect with a line in space, in a plane, okay? To draw something. So I'm going to say this is R1, this is R2. Everything in the middle, all of this dot in the middle is going to be expressed by R. Now, the way the computer actually draw a line is that if you click these two dots, okay, you just change the lambda here, which is this is a parameter. That's why the main parameter line right there. Lambda changing from 0 to 1. So when the lambda is 0, what would be the value of lambda R here? R1. R1? Or R2. R2 or R1? R2. R2 right there. How about lambda is equal to 1? R1. So basically, what it does is that as you change your lambda, computer can find out that the dots, interpolating dots in the middle between these two lines, a line in one line. That's basically what we call a parametric line. Okay, that's how the computer generates lines in the plane, on a screen. And there are many things we can do with this. There are several things we can do with this parametric line formation. One of them is the collision check. So again, this is a practical way of presenting line on screen. Now, one of the things that we can do with this formation, collision check, or membership testing. Membership testing is something that we already studied in the previous chapter. Membership testing means that if I have some shape like this, and if I have a line goes somewhere that belongs to something else, are they colliding to each other or not colliding to each other, or what is the gap between these? Because it is important for us to calculate torus. And sometimes you have to make sure that when you put things together, you may, by accident, put them too close to each other so that they actually overlap. Then it may not be function as it is designed. So membership testing is very important. So collision checking is one of those membership testing. And then if you express line with this parametric line formation, the collision test is very easy. I'm going to show you some examples. For example, let's say you have two lines in X, Y. You have two lines right here. And this line will be, the first one is R1, R2, for example, R1, R2. And the second line is expressed by R3 and R4. Okay, R3 and R4. And then you need to have two parameters to express these two lines. One, I'm going to say is lambda, the other one is mean. Just two lines, two different parameters. Okay? And then if they collide to each other, on a plane, you can figure this out by saying, okay, say this is the, I'm going to say this is R1 prime, this is R2 prime. Prime means that this one right here to differentiate from the actual control points. So I'm going to have to say R1 prime and R2 prime should be equal if they collide at some point. At some point, right? At some point. So what we can do is that you actually develop equation for two individual lines and then equalize them together. Such as, so we have a R1 prime, for example, is lambda R2 plus minus lambda R1. R2 2 prime is going to be mu R4 plus 1 minus mu R3. Let's say you have 2 project lines like this, defined by the 4 control points. Okay? And if I equalize this together with this, what's going to happen? You just have to say lambda R2 plus 1 minus lambda R1 is equal to what? Mu R4 plus 1 minus mu R3. If we equalize it together, right? I'm trying to solve this problem, the equations. And then what I'm going to do is to collect the terms with the same common parameters, lambda right here, mu right here. I'm going to just collect them all together. So if I collect them all, it's going to be R2 minus R1 lambda, right? R2 minus R1 lambda. And then I'm going to bring this R4 and R3 to the left-hand side, so it has to be negative R4 minus R3 mu. And then I'm going to bring the rest of them, the constant, one without the lambda to the right-hand side. So that's going to be R3 minus R. Correct? R3 multiplied to 1 and then R1 multiplied to 1 that goes to the right-hand side. Okay? So I just rearrange them together. In this format now, if you solve this problem, you can find the parameter lambda and mu. These two parameters.
Is that an addition or a subtraction in between lambda and mu?
Well, I just equalize it together. So, you mean this one here?
Yeah.
Well, the reason is for this negative is because I take this to the left-hand side. So positive becomes negative.
Okay.
That's simple, just transition. And then if you understand the x1 point system, each R has what? R1 has what? X1 component and Y? How about R4? X? 4, Y, 4. And then it goes on like this. So this equation is not just a simple equation, but it has the x2 minus x1, y2 minus y1, lambda, minus 1. This is x4 minus x3, y4 minus y3. Mu is equal to x3 minus x1, y3 minus 1. Now, how many equations do we have?
My question real quick is where it says R2 prime? Right there?
This one here?
No, lower. Two lower. One up.
This one here? Yeah.
Right there, where it says 1, is it 1 mu or is it 1, supposed to be 1 minus?
1 minus. So, 1 minus. It's the same format, but it's a different parameters. So, how many unknowns do we have here? How many unknowns in this equation? What are we looking for? What are we trying to find out? And then the parameters, right?
Yeah.
And then how many equations?
2.
1 or 2? 2. There's one is for x equation. The other one is for y equation. I have 2 equations. So can I solve it or not? You should have to solve it because number of unknowns is the same as the load, the number of equations. Okay? So statically deterministic. So if this is the case, then you can find lambda and mu somehow. And then one thing you can say is that what was the valid range of lambda and mu? When I describe this parametric line, what is the valid range of lambda and mu? The parameter has to be always from 0 to 1. Okay? Meaning that if they are colliding each other like this by this equation, okay, by this equation, if you solve for lambda and mu, the range of lambda and mu has to be between, both has to be between 0 and 1 to be valid. And if for some reason their range is not in between 0 and 1, then you can say they are not colliding each other. Okay? That's basically simple collision check or membership test by using this format of the parametric line. Okay? So let me give you some homework right here. Oh, maybe it's not, maybe that's a solve one problem here. If you have the, say if you have zero comma zero, this was 4 comma 0. So we have 2 lines. Here's your R1, this is R4, R2, this is R3. So by looking at this picture, most of you guys can say, well, they're colliding each other. The computer is not smart enough to tell because it has no eyes. It has to do by what? Going for some values. Okay? So somebody has to solve these equations to see if they are colliding to each other. Well, okay, so if this is the case, what I can do is just set up an equation. By using that equation, x2 is what x2 is. 4, right? 4, x2 is actually power, x2 is from R2. Y2 is from R2, right? So 4 minus what? X1, which is? 0. Another one, Y2, 3 minus 0. Lambda minus X4, 4, Y4, 0 minus X3, 0 minus 3. Mu is equal to, what is it now? X3, 0, 3 minus X1, 0. That's your equation. But there are 2 equations, one for X and one for Y. Okay, how to solve it? 4 lambda minus 4 mu is equal to 0. It's the first equation. Second equation is 3 lambda plus 3 mu is equal to 3. The second equation. Can I solve for this? How do I solve it? Well, from first equation, if you take this guy to the right, you say 4 lambda is equal to 4 mu, right? So if you cancel this out, that means lambda has to be equal to mu. That's one thing. And if you replace this mu with lambda now, because we know that lambda is the same as mu, that's 6 lambda is equal to 3. So lambda, what is lambda? 1 0, right? 1 over half, 1 over 2. Which is equal to mu. So is that are they in the range of 0, 0 and 1?
Yes.
Yes. So the computer can say, hey, they are colliding to each other. Okay? So if this is not done on purpose, the computer has to reject or cause, report error in your drawing. I mean, if you have millions of those lines to draw a F-14 Tomcat, for example, okay, you can't do it by hand, by vision. Even if you are smarter than computers by looking at, if there is a colliding lines in there or not. The computer is so fast. The computer can do millions of times of the calculation like this in a couple of seconds, right? So just leave it there to computers, and the computer actually do everything by this calculator. Yes.
My question is, when you wrote the equation 3 lambda plus 3 mu equals 3, why did you also off-write from the mu, you wrote the lambda symbol? Is it just because they're the same?
Oh, no, what?
On where you wrote 3 lambda plus 3
This
mu,
one?
yeah, on that one.
Uh-huh.
Why is it on 3 mu you also wrote the lambda symbol?
This
Is it
one
just
here?
saying they're the same?
Yeah, the same. If they're the same, I just put lambda. I'm just going to replace them. Because from the first equation, we found that the lambda and mu has to be equal. Because if you take this part to the right,
Oh, so it's just
4 lambda is
substitution.
equal to 4 mu, right? And we cancel each other, that's lambda should be equal to mu. So in the second equation, I'm going to just apply this finding from the first equation to the second equation. So the set 3 lambda plus, instead of mu, I'm going to just replace mu with lambda. It's just to solve for lambda, okay? That's how you solve it. Or if you know how to solve them by matrix, go for it. Whatever you feel comfortable with, go. You can use it. All right? Another question? No question? So this is how computer actually do the membership testing for your drawings.
I have a question.
Yes.
So is that a general formula, x2 minus x1, y2 minus y1?
This
Right,
one?
it's yes.
Yeah.
So does it matter the orientation, like, because in the first, graphic you had R2 and R4 in different positions?
Only thing you have to be sure about is that the line, okay, the first line should go with R1 and R2. You can't go with R1 and R3 or R1 and R4.
Okay.
Okay, if that's the case, you have to develop this again, because if that's the case, you just set this up and develop your own equation.
Okay.
But if you want to stay with this equation, just make sure that you have the one line with R1, R2, then line with R3 and R4. If that's the case, you can stay with this.
Okay.
Otherwise, you just go back to this and then solve it. Set up your own equation, okay? Set up the equation and solve it. Any other question? That's a good question. Anything else? All right, move on to the, I think that's pretty much about reviewing the line. Before I move on, let's just assign some homework real quick. To practice this at home. So again, this is the first line here, line 1, and this is line 2. Again, as long as they are staying with R1 and R2 belongs to one line, and then R2 and R4 belongs to another line, and stay with this equation right here. Otherwise, or you can just develop your own code.
You write that like somewhere else.
The computer is in a way.
Oh, computer?
See?
Yes.
You see?
Probably got it.
Huh?
I can. Where?
Yeah.
I'm not sure.
It's 1043
R1,
4125.
R2, just calculate. That would be the line one.
Okay, let's move on to the curve theory now, because now we understand what the parametric line is all about, why computer uses parametric lines, and then we dealt with one of the functions that computer does with this parametric line structure. So I think we're ready to move on to the physics spline curve. Okay, so in Hermite spline curve, the different number of the cubic spline curve is the Hermite spline curve. And then what basically it does in Hermite spline curve is that you have for example, as we did on the line, we basically define some control points, whichever number of control points you define. You basically tell the computer to connect all these dots with a smooth spline curve, okay, spline curve. So the result of the spline curve, if you do so, is going to be something like this. Okay, something like this. But for the D-spline curve, if you use B-spline curve, major spline curve, do the same. I want to show you the difference between this spline curve and Hermite spline curve and Bayes spline curve, just before we actually study the actual theory behind it. So what's going to happen for the Bayes spline curve is the curve itself will be something like this. What's the difference between each of them? What's the difference? You see the difference?
Intersectional point.
Well, the Hermite spline curve actually goes going through the points, okay, touching each point. But in Bayesian spline curve, it's not going to touch those control points. It's going to go somehow curve smoothly with these around this curve, around these control points. That's the result. Okay. And then we'll see why this is happening, and then what's the advantages, pros and cons of each control point. And you should be able to selectively use them to fit them into your own application. Okay. And most likely, for the Hermite spline curve, it's not working well. Anybody has some driving better than this? This is maybe better. Hermite spline, okay. What people do is to use the equation of third order polynomial curve, third order